You are listening to The Deep Learning Revolution by Terrence J. Sejnowski. Watch a child learn to identify their mother's face. No complex algorithms guide this process, just constant exposure to visual information that gradually shapes their recognition abilities. Computer scientists spent years taking the wrong path. They constructed elaborate rule systems to teach machines facial recognition, defining precise measurements for eye distances and nose proportions. These efforts consistently disappointed. A revolutionary group of researchers questioned this entire methodology. What if machines developed intelligence through data immersion rather than programmed instructions? This single insight changed everything. Modern smartphones instantly translate foreign languages. Autonomous vehicles navigate city streets. Digital assistants comprehend questions and provide meaningful responses. Gaming programs defeat human experts at incredibly complex strategic challenges that traditional coding could never handle. The transformation started when neuroscientists partnered with computer engineers in research labs. Together, they studied authentic brain learning mechanisms. Nature required millions of years to evolve intelligence. Artificial systems accomplished similar feats within mere decades. Picture artificial intelligence in the 1980s as a massive cathedral where everyone chanted the same doctrine. Construct better databases, develop stronger logical frameworks, write more comprehensive rules. The AI priesthood insisted computers must process information like rational philosophers, manipulating symbols through rigid methodologies. Teaching a computer to identify cats meant programming specific characteristics, pointed ears, whiskers, fur textures. This methodology seemed reasonable and sophisticated. Humans could articulate their thought processes, so machines should operate identically. Unfortunately, results remained consistently poor. While mainstream AI researchers reinforced symbolic reasoning approaches, a small group of mavericks explored forbidden territory. These scientists proposed a scandalous concept. Computers should process information like infants, not philosophers. Terry Sejnowski represented these rebels. Collaborating with researchers including Jeffrey Hinton, he examined history's most successful intelligence system and posed a fundamental question: how do brains actually function? The answer proved revolutionary. Brains operate without programmed instructions. Billions of basic neurons create connections, learning through direct experience. Consider bicycle riding. Balance cannot be programmed through rules, yet brains master this skill through repetition. You stumble, make corrections, stumble again, adjust further. Eventually, neural pathways encode successful balance patterns without anyone writing explicit instructions. These AI revolutionaries termed their approach connectionism, and the establishment despised it. University funding disappeared. Academic conferences rejected their research. Critics condemned neural networks as evolutionary dead ends, claiming they lacked sufficient complexity for genuine intelligence. However, these rebels recognized something crucial. Nature had already mastered every problem that stumped traditional AI systems. Birds navigate using visual processing. Infants acquire language through auditory input. Animals instantly recognize threats. No programmer taught these capabilities through logical frameworks. If biological computers inside human skulls could handle speech, vision, and sophisticated reasoning, why couldn't silicon-based systems achieve similar results? Early AI rebels believed the solution lay not in superior programming, but in enhanced learning methodologies. Their intuition proved correct. First, they needed to decode how biological learning actually operates. The answer emerged from studying 3 pounds of the universe's most mysterious matter, human brain tissue. Picture recognizing your grandmother's voice through poor phone connections. Your brain doesn't reference databases of vocal characteristics and accent patterns. Instead, elegant processes unfold. Millions of neural connections strengthen each time you hear her speak, while others weaken. Over time, your brain constructs her unique vocal signature that functions even through static interference. This phenomenon fascinated AI revolutionary scientists like Sejnowski and Hinton. They discovered that biological learning functions like massive democracies, where simple neurons vote on perceived experiences. Individual neurons don't possess complete answers, but their interconnections generate intelligence. They constructed artificial, programmed versions of these biological networks. They designed mathematical neurons that could strengthen or weaken connections based on experience, mimicking real brain cells. When they provided thousands of examples to these networks, remarkable events occurred. Artificial neurons self-organized to recognize patterns without explicit programming. Think about spotting friends in crowded airports. Brains don't follow feature checklists. They process complete pictures simultaneously, combining height, walking style, and posture into instant recognition. The AI rebels constructed networks that operated identically, processing information through layers that progressively developed understanding. One breakthrough emerged from studying how brains handle contradictory information. Real neurons sometimes activate randomly, appearing to flip coins. This seemed like design flaws until researchers realized randomness was actually advantageous. Random firing helps brains escape suboptimal solutions and discover superior ones, like shaking marble jars until they settle into efficient arrangements. Sejnowski and Hinton captured this insight in Boltzmann machines, named after physicists who studied particle arrangements. These artificial networks learned by testing different solutions and gradually settling on optimal ones, exactly like brains solving puzzles. The real revolution arrived when they solved the learning mechanism itself. They determined how to make artificial networks automatically adjust connections when making errors, strengthening pathways leading to correct answers while weakening incorrect ones. This process, called backpropagation, taught networks to learn from their mistakes. The fundamental insight proved profound. Intelligence involved discovering patterns in massive data quantities rather than following predetermined rules. Provide biological brains with sufficient examples, and they learn to see, hear, and understand. Feed artificial networks enough examples, and they achieve identical capabilities. For decades, AI rebels possessed correct concepts about advancing machine learning, but lacked computational power to demonstrate them. Their neural networks resembled formula, one-race cars equipped with bicycle engines. They understood their designs worked, but needed substantially more fuel, bigger engines, and longer racetracks to prove their machines' true potential. Three forces converged to create perfect conditions. Computer chips became exponentially more powerful, especially graphics processors originally designed for video games. These chips performed thousands of simultaneous calculations, exactly what neural networks required. Internet expansion created data mountains. Every uploaded photo, search query, and mouse click became training material for hungry algorithms. Researchers refined learning techniques, making networks deeper and more sophisticated. The breakthrough moment arrived when researchers fed massive datasets into these supercharged networks. Suddenly, artificial intelligence accomplished seemingly impossible tasks. Consider image recognition transformation. Traditional programming required engineers to manually code features like edges, corners, and shapes. This resembled describing every possible cat recognition method without showing computers actual cats. Results remained mediocre. When researchers fed millions of labeled images into deep neural networks, magic occurred. Networks learned to recognize cats, dogs, cars, and faces with superhuman accuracy. They didn't memorize training images, but extracted essential characteristics that define cats as cats. Show them previously unseen cats in any pose or lighting, and they recognized them instantly. Google Translate transformed overnight from clunky phrase books into near-fluent translators. Analyzing millions of translated documents, deep networks learned hidden patterns between languages. They discovered that concepts like love, freedom, and justice occupy similar positions in different languages, mathematical spaces, even when words sound completely different. Gaming provided the most dramatic evidence. In 2016, a deep learning system called AlphaGo defeated the world champion at Go, an ancient strategy game more complex than chess. Go contains more possible board positions than atoms in the observable universe. Traditional programming couldn't begin tackling such complexity, but deep learning thrived on it. Self-driving cars began navigating real roads, recognizing stop signs, pedestrians, and other vehicles in real time. Voice assistants started understanding natural speech and responding appropriately. Financial algorithms began detecting fraud patterns that human experts missed. AI rebels had waited 30 years for this moment. Their networks finally possessed sufficient power, data, and sophistication to prove machines could learn like biological brains. The revolution was no longer theoretical, but actively reshaping the world. Despite breathtaking AI advances, one crucial element remains absent. Current systems resemble brilliant students who have memorized textbooks but never left classrooms. They recognize millions of images, translate numerous languages, and defeat world champions at complex games, yet lack something every toddler possesses: direct sensory world experience. Consider 2-year-old learning processes. They crawl, touch, climb, taste, and explore. When learning hot, it's not vocabulary symbol, but memory connected to pulling hands from scalding stoves. This embodied learning creates rich, interconnected understanding that current AI systems cannot match. Human intelligence emerges from physical world interactions. We learn objects fall when dropped, pushing harder accelerates movement, and other people possess different thoughts and feelings. These seem simple but form common sense foundations that even advanced AI models struggle with. Ask humans why someone carries umbrellas on sunny days, and they'll quickly suggest expected rain. Ask AI systems identical questions, and they provide statistically probable answers without truly understanding concepts. Humans excel at intuitive leaping because learning is grounded in physical experience and social interaction. Emotions play an essential role in human intelligence. Fear helps avoid danger, curiosity drives exploration, and empathy enables understanding others. Rather than intelligence obstacles, they're integral components. They guide attention, shape memories, and influence decisions in ways logic cannot. Most importantly, humans continue learning throughout lifetimes. Children who learn walking don't stop adapting movement when encountering stairs, uneven ground, snow, or ice. They continuously adjust, building on previous experience while remaining flexible enough to handle new situations. AI researchers who started this revolution understood something critical. Studying human intelligence wasn't about copying it, but understanding what makes learning possible. Today, conversations flow both ways. Deep learning advances help neuroscientists understand brain functions, while biological intelligence discoveries continue inspiring new AI architectures. The gap between artificial and human intelligence remains vast but narrows constantly. The question isn't whether machines will match human intelligence, but what new intelligence forms might emerge when silicon and carbon-based learning systems collaborate. The deep learning revolution that began with rebels studying brain functions has become our era's defining technology. Whether it enhances human potential or disrupts society depends largely on today's choices. The conversation between silicon and carbon intelligence has just begun, and we'll all write the next chapter together. Scientists already develop systems that learn continuously, adapting to new situations without forgetting previous ones. Medical AI spots diseases in X-rays that human doctors miss, and climate models powered by deep learning predict weather patterns with unprecedented accuracy. Personalized education systems adapt to individual learning styles, making quality instruction available globally. Rapid progress brings profound challenges. Students can generate entire essays with keystrokes, forcing educators to rethink critical thinking and creativity instruction. Technology making learning accessible also makes cheating effortless. Job markets face similar disruption. AI systems handle customer service calls, analyze legal documents, and create marketing content. While new jobs emerge in AI development and oversight, traditional roles disappear faster than retraining capabilities. The challenge extends beyond technology to humanity. How do we help millions of workers adapt to rapidly changing economies? Most concerning is AI's ability to create convincing fake content. Deep learning generates realistic videos of people saying things they never said, writes authoritative-sounding news articles containing fabricated facts, and creates social media posts designed to manipulate public opinion. When anyone can create believable lies at scale, distinguishing truth from fiction becomes critical survival skill. Yet identical technology offers solutions. AI systems detect deepfakes, flag misinformation, and help fact-checkers verify claims faster than ever. The key lies not in restricting AI development, but ensuring it supports human flourishing. Looking ahead, researchers work toward AI systems combining deep learning pattern recognition with human-like reasoning and common sense. Imagine AI assistants truly understanding context, robots learning by watching and questioning, or medical systems explaining diagnoses in terms doctors and patients trust. AI rebels who first sought biological inspiration gave us tools to reshape intelligence itself. Now it's our responsibility to use them wisely. You've learned that the journey from studying baby brains to creating AI traces one of history's most profound shifts. A small group of researchers who dared challenge conventional wisdom discovered that intelligence emerges from recognizing patterns in vast data amounts, not from following logical rules. Today, deep learning systems translate languages, diagnose diseases, and solve problems that seemed impossible decades ago. Yet as these technologies reshape education through employment, we face important choices about harnessing their power while preserving uniquely human qualities. The revolution that began by copying nature's most successful design now offers us opportunities to thoughtfully guide intelligence's future. Found these insights valuable? Hit like and subscribe for book summaries that could transform your thinking. The purchase link for the Deep Learning Revolution is waiting in the description, and we're curious, which of these concepts resonated most with you? Drop a comment below.